In programming, it only takes a split second, a single moment where two things try to grab the same resource to turn a beautiful application into total chaos. So today, we're going to dive into thread synchronization. It's really the art of taming that chaos and bringing in some precise, reliable control. Let's jump in. So, what happens when everyone rushes for the same thing at once? I mean, you've seen it, right? Black Friday sales, cars jamming into a single lane. It's a mess. Well, guess what? The exact same thing happens inside your software. You have these multiple threads. You can just think of them as little workers running around. And when they all try to mess with the same piece of data at the exact same time, yeah, you get chaos. And we're not talking about a little tiny mess here. This is digital chaos. It leads to your data getting totally corrupted, your app acting in these bizarre, unpredictable ways, and yep, even flat-out crashes. It is absolutely the kind of bug that keeps developers staring at the ceiling at 3 a.m. So the big question is, how do we stop it? All right, here's our game plan for untangling this whole thing. First up, we'll look at the race for resources. Then we'll see how the solution can sometimes cause a deadly embrace. After that, we'll check out the different locks for every door, figure out how to unlock peak performance, and finally, we'll cover the one single, unbreakable rule you've got to follow. Okay, first section, the race for resources. Why can't we all just have it at once? Well, at its core, the problem is super simple, right? You've got one valuable thing and a bunch of different processes all trying to change it at the exact same moment. That is just a recipe for disaster.
Let's make this really concrete. Imagine a library, and in this library, there's one priceless single copy book. Now, all these patrons, our threads, want to read it, or even trickier, write in it. What happens if two people try to write their own notes on the same page at the same time? It's just going to be an unreadable scribbled mess, right? Well, that's exactly what happens to the data inside your application.
And this is where our main idea comes in, thread synchronization. Really, it's just the process of managing who gets access. It's the set of rules and tools that act like a librarian, The librarian who says, hey, one at a time for writing in the book. This isn't just a nice-to-have suggestion. It's a totally mandatory system you need to keep your data from turning into that scribbled mess. Okay, so how do we do this? Well, the most common way is with something called a lock. It's simple. Only the thread holding the lock can get to the resource. Sounds perfect, right? A great solution. But what happens when the cure actually becomes the disease? What if the very thing meant to create order creates an even worse problem? And trust me, this is no small thing. Our sources are really clear on this. Deadlocking is a significant danger in synchronized code. It's like this silent trap waiting to spring, and when it does, it can bring your entire application to a complete grinding halt. So let's break down exactly how this digital standoff happens. Let's go back to our library to see this in action. Okay, picture this. Now we have two important things, the book and the only pen in the library. Patron A walks in and grabs the book. At pretty much the same time, patron B grabs the pen. Now patron A wants to write in the book, but they need the pen, and B has it, so patron A is stuck, just waiting. But then, and here's the kicker, patron B needs the book to know what to write, but A has it. See the problem? They're both completely blocked, each waiting for the other. Nothing is ever going to happen. That, my friends, is a deadlock. It's a total digital standoff. You've got two or more threads just frozen in time, each one holding something the other one desperately needs, and they're waiting for a release that is literally never going to happen. So, how on earth do you prevent this kind of catastrophic freeze? Well, the solution is actually surprisingly simple, but it requires discipline. You have to set up a strict protocol, a rule. For example, everyone has to agree you always acquire the lock for the book first, and only then do you acquire the lock for the pen. If every single thread follows that exact same order every single time, a deadlock like the one we just saw becomes impossible. That's the key right there. Consistency is everything. Okay, so we know we need locks. But here's the thing. Not all locks are the same. Just like a locksmith doesn't use the same tool for a car door and a bank vault, a developer has a whole toolkit of different synchronization tools, and each one is designed for a very specific job. So let's take a quick look at this developer's toolkit. First, you've got the Mutex. This is your heavy-duty general-purpose lock. It's so powerful, it can even work between two totally separate programs. Then you have the Semaphore. The best way to think of this one is like a bouncer at a club with a velvet rope. It only lets a certain number of threads in at a time, maybe 3, maybe 10. After that, there's T-Monitor,
which is this really simple and efficient lock that's built right into objects inside a single program. And finally, for super, super short waits, you have the spin lock. Instead of going to sleep, the thread literally just spins in a little loop, asking, is it free yet? Is it free yet? So yeah, different tools for different problems.
All right, so we've got all these tools to keep our code safe, but what about making it fast? Because sometimes a simple general-purpose lock is just too heavy. It can really slow things down. So let's look at a really clever, specialized solution for a super common situation.
Let's head back to our library. Imagine this. 99% of the time, people coming in just want to read the book. It's only very, very rarely that some scholar needs to actually write a new note in it. So, does it really make sense to make everybody get in a single file line one at a time if most of them are just reading? I mean, why can't all the readers just look at the book together at the same time? Well, that is exactly the problem a reader's writer lock was invented to solve. It's a really smart lock that has two different modes. If you just want to read, it's like, come on in, all you readers are welcome. But the second, and I mean the second, someone shows up who needs to write, the lock basically puts up a big stop sign. It waits for all the current readers to finish up, and then it gives that one writer completely exclusive access. And the difference this makes for performance? Oh, it's absolutely staggering. In a situation with tons of reads and only a few writes, a regular, standard lock creates this huge bottleneck. It just crushes your throughput. But the reader's writer lock, it opens the floodgates for reading, letting tons of threads work in parallel. The result is just massively higher performance. It's the perfect example of how picking the right tool for the job can really unlock incredible speed. Okay, we've talked about what to lock and how to lock it to avoid deadlocks. But that leaves one last and I mean absolutely critical question. What happens if something goes wrong? If your code throws an error while it's holding a lock? Just think about that for a second. Our patron has the book, they've locked it, they're about to write, but oh no, their pen runs out of ink. That's an unexpected error, right? Now, if they just get frustrated and walk away, what happens? The book is still locked, forever. Nobody else can ever use it, and the whole library just grinds to a complete standstill. And that right there is why good, robust code always uses a safety net. In a lot of programming languages, this is what's known as a try.finally block. The idea is simple. You put all your important work inside the try part, and you put the code to release the lock in the finally part. And here's the magic. That finally block is guaranteed to run, no matter what. Even if your code crashes and burns with an error, finally will still execute and release that lock. So here's the pattern. It's beautiful in its simplicity. You acquire the lock before you enter the try. You do all your critical work inside the try, and then you release the lock inside the finally. This simple pattern, this is really the cornerstone of safe, multi-threaded code. It is your guarantee that a lock is never, ever left behind. So the takeaway couldn't be clearer. If you don't use this safety net, you are always risking a permanent lock that freezes your entire program. But with it, you get a guaranteed release and code that can actually handle errors gracefully. It's truly the difference between brittle, amateur code and solid, professional-grade software. So there you have it. From stopping the initial chaos of a resource race, to sidestepping that deadly embrace of a deadlock, and all the way to picking just the right lock to maximize performance, thread synchronization is really all about being a good architect, building smart, well-managed doorways to your data. So now you've got the keys. The only question left is, what doors are you going to build that are both perfectly safe and incredibly fast?